Hello everyone, I'm Serena Su and welcome to our journey into the world of meteorology. Today, we're diving deep into the importance of humidity and its pivotal role in weather forecasting. Humidity affects everyday life, from static electricity to how quickly our clothes dry, and it's crucial for understanding cloud formation and weather changes. We will discuss two fundamental concepts of humidity, absolute and relative humidity, and how we measure it using modern instruments. Then we'll explain what saturation and dew point mean, and show how these concepts help meteorologists predict the weather, particularly how clouds form and how different types of clouds can indicate upcoming weather changes. So get ready to uncover the scientific mysteries behind this weather phenomena as we explore how to better predict and prepare for the weather ahead. Let's kick off this exciting learning adventure. Concepts and impacts of humidity. Let's talk about humidity, a key meteorological factor that affects our daily lives, particularly in Taiwan. Humidity directly influences our everyday activities. Humidity significantly affects the occurrence of static electricity. We often notice that during dry seasons, the low humidity makes it difficult for charges to neutralize, leading to frequent static shocks. You might have experienced this discomfort or even slight shocks when touching doorknobs or other objects. In Taiwan, the level of humidity also positively impacts agriculture and ecology. High humidity helps keep the soil moist, reducing the need for irrigation, which is especially crucial for water-dependent crops like rice. Moreover, a humid climate helps protect natural vegetation and support biodiversity. Now let's quickly go over two fundamental concepts of humidity: absolute and relative humidity. Absolute humidity refers to the actual weight of water vapor in the air, telling us how many grams of water vapor are present per cubic meter of air. Relative humidity is the percentage of water vapor in the air compared to what the air can hold at the temperature. When relative humidity reaches 100%, the air is saturated, and any further cooling will cause the water vapor to condense into dew or form clouds. Methods of measuring humidity. So how do we measure humidity? There are three main methods. 1. Digital hygrometer. This device uses electronic sensors to detect moisture in the air and provides precise, real-time data. It's ideal for laboratories and industrial settings where quick and accurate humidity readings are crucial for controlling experimental conditions or production quality. 2. Wet and dry bulb thermometer. This traditional tool uses two thermometers, one dry and one covered in a wet cloth. It calculates relative humidity by comparing the temperature difference between the two. The dry bulb measures the air temperature, while the wet bulb is cooler due to evaporation. This thermometer is great for outdoor or remote area as it doesn't require electricity. 3. Electronic hygrometer. Electronic hygrometer use advanced sensors to detect changes in air moisture. This device can be connected to computer systems to automatically log and analyze data, helping scientists and meteorologists accurately predict weather changes. For instance, using this data in climate models can forecast weather trends for the upcoming months. These tools are vital for understanding the predicting weather changes, helping us better plan and adapt our daily activity to stay comfortable and safe in various weather conditions. Saturation, dew point, and weather forecasting. After learning about different tools to measure humidity, let's explore how humidity affects weather forecasting and the roles of saturation and dew point. Humidity is an indispensable element in weather forecasting, directly affecting cloud formation, rainfall, and other weather phenomena. Meteorologists closely monitor humidity changes to predict upcoming weather conditions. Saturation occurs when the air contains the maximum amount of water vapor it can hold. When air becomes saturated, any additional cooling will cause excess water vapor to condense into droplets, forming clouds and precipitations. This is the basic principle behind how clouds and rain forms. The dew point temperature is a critical measure of when air becomes saturated. It indicates the temperature at which water vapor begins to condense. Understanding the dew point is crucial for predicting the formation of fog and dew, which often occur during cooler night or early morning hours when the surface temperature drops below the dew point. On the right side here, we have two images to look at. In image A, we see polar air where the air temperature and dew point are the same, both at -2 degrees Celsius, and the relative humidity has reached 100%. Under these conditions, on a chilly morning, water vapor in the air easily reaches saturation and condenses into fog, creating dense fog. This is crucial for morning traffic safety as dense fog significantly reduces visibility. In contrast, image B shows a desert setting where the air temperature is a scorching 35 degrees Celsius. The dew point is just 10 degrees Celsius and the relative humidity is 21%. These conditions indicate an extremely dry climate, predicting continued clear and dry weather, with little chance of rain. This is vital for planning outdoor activities or agriculture operations. By continuously monitoring humidity, saturation, and dew point, meteorologists can provide more accurate weather forecasts, helping us plan daily activities and prepare for potential weather changes. Formation and classification of clouds. Having understood how humidity, saturation, and dew point influence weather predictions, let's delve deeper into how these conditions facilitate cloud formation. When water vapor in the air reaches saturation and begins to condense, we witness the natural beauty of various cloud types. Let's examine how clouds form and how their different types impact our understanding and predictions of weather. Cloud formation starts with the evaporation of water from the surface. As this water vapor rises with the air and reaches cooler altitudes, it cools down to the dew point temperature where it condenses into tiny water droplets or ice crystals, forming cloud droplets. These droplets gather together, and when they reach a certain size and weight, they form clouds visible from the ground. Clouds are classified based on the conditions that form them. Cumulus clouds. These clouds typically form during active convection days when warm, moist air rises rapidly and condenses upon encountering cooler air. Such clouds often indicate atmospheric instability and may develop into thunderstorm. Stratus clouds form under more stable atmospheric conditions. These clouds often cover the sky extensively, bringing continuous light rain or overcast weather. Cirrus clouds. Found at high altitudes, these clouds are composed of ice crystals and their delicate, ribbon-like appearance often signals the approach of a storm. By observing these clouds and their changes, meteorologists can predict upcoming weather conditions, providing accurate weather forecasts. This knowledge is not only vital for meteorologists, but also crucial for the safety planning of industries like aviation and maritime. So, understanding the process of clouds formation and the types of clouds helps us better prepare and respond to potential weather changes, enhancing our decision making in daily life. Finally, today we've delved deep into the understanding of humidity and cloud formation, which are crucial for understanding and predicting weather changes. Grasping the scientific principle behind this natural phenomena is vital for our weather forecasting and the study of Earth's climate. So next time you look up the sky and see clouds of different shapes and types, try to interpret the weather information they convey using the knowledge you have learned today. Thank you so much. Thank you all for watching, and I'll see you next time. Bye!